Okay, we're looking at the last set of notes in this section on applications of the derivative. This is going to be called the mean value theorem, also known as MVT. Okay, so this theorem is one of the bigger ones, but before we get to it, we're going to need a bit of what's called a lemma, and the lemma here has a name. It is called Rolle's theorem. Okay, so Rolle's theorem is something we're going to prove first in order to get to the mean value theorem. Rolle's basically says if I have a continuous function on the closed interval AB, and it also has to be differentiable on the open interval AB, then there has to exist a C on the open interval such that, I'm sorry, we're missing a condition there. We have to have the functional values f of A has to be equal to f of B, and then if I have that, there has to exist, then there exists C on that open interval AB, where f prime of C has to equal 0. Okay, so what are we saying here? I have some sort of function, let's call it f, right? So here is my function f, and if I size up the right points here, I have a closed interval starting at A and ending at B, where f of A and f of B are equal, right? So these are at the roughly same height is the idea here. So if these things are at the same height, then there has to be a point somewhere along the line, and in this case there's going to be two of them, so maybe we'll just call this one C, where the derivative f prime of C has to equal 0. So if we've got two things that are equal, the two ends of the interval are equal, then there has to be a point somewhere along the middle where that derivative is 0. We're going to prove this by cases. Okay, so the trivial case is case number 1, where I just have a constant function, right? So here's my interval A, B. I have a constant function, and therefore f of A is equal to f of B. It's continuous, it's differentiable. Well, every single point in the constant function, so no matter what C I pick, f prime of C has to equal 0. So this is true for all C on AB. So that's an easy case. All right. Case number 2, we start here, we end here. We have A, we have B. And at some point, there's going to be a value x, which is bigger than A and B. Okay, so if that's the case, I have some value x up here that's bigger than A and B, right? So f of x is clearly larger than f of A, which is equal to f of B. Okay, so if this is the case, then I'm guaranteed that on the closed interval from A to B, there must be a maximum, right? Because that's by EVT. If I have a closed interval from A to B, a maximum must exist. Well, since f of x is bigger than both of these, that tells me that the maximum isn't at A and it isn't at B, which means there has to be some other point C, which is between A and B, where there is a maximum. And that maximum has to be an absolute maximum, but it's also going to be a local maximum, right? Or a relative maximum, right? Relative or local maximum, which in our drawing here, that point looks like it's like here, right? Okay, so if I do that, then what I also know is there is, at that point, so let's call that value C, f prime of C has to be 0. Because if there is a local maximum on a differentiable function, then the derivative at that point has to be 0, so says Fermat. Okay, so the third case is the only other option. I have a point A, I have a point B, and there's some point X that where f of x is less than f of a. That works exactly the same as case 2, but instead of having a local max by EVT, there exists C where A and B, where we have a local min, and if I have a local min, also by Fermat, that thing has to have a derivative of 0. Okay, so these are my only 3 possible cases. Either the point is always equal to A, or f of A and f of B, or there's at least one point where I'm above f of A and f of B, or there's one point below f of A and f of B. In all 3 of these cases, there has to be a point along the way where the derivative is 0. So using those 3 cases, which are the only 3 possible cases, we have now proven Rolle's theorem. All right, so let's work a quick example of where Rolle's theorem might apply. Let's say we have x cubed plus x minus 1 equals 0, and we want to prove that it has exactly 1 root. Okay, so I know this. If I let f of x be x cubed plus x minus 1, and I pick f of 0, that's clearly equal to negative 1. And if I pick f of 1, then I get 1 cubed plus 1 minus 1. That's 1, which means that between 0 and 1, I've crossed from negative to positive, and this is a continuous differentiable function. So by IVT, the intermediate value theorem, there has to equal C on the interval from 0 to 1, such that f of C is 0. Okay, so this tells me that I have a root. Okay, now what we've got to show is that that root is in fact unique, and it's the one and only one root. Okay, so the way we do this is suppose not. Suppose there is D not equal to C, where f of D is also equal to 0. So let's suppose there's another root. Okay, so this would mean that there, by Rolle's, there has to exist some k on the interval CD, or it could be DC if D is less than C, right, where the derivative of k is 0. Because, see, these are both equal to 0, right? That's annoying. So this says that f is equal to 0 at C, f is equal to 0 at D, which means that f of C and f of D are equal, which means that on the interval between them two, there has to be a point where the derivative is equal to 0. And so we just proved a minute ago in Rolle's theorem. Okay, but let's take a look at the derivative of this thing. If I take f prime of x, right, that gives me 3x squared plus 1. Aha, well this is always positive times 3, right? So at least it's non-negative times 3 plus 1 means that thing's always greater than 0. Aha, we have a contradiction here. So if I allow for there to be a second root, and we know that 1 has to exist, we've proven that up here, by the intermediate value theorem, if there is a second root, then these two things would have to be true at the same time. But see, there would have to be something with a derivative equal to 0. There can't be any point between c and d where the derivative is 0, because the derivative of this thing is always positive. This function, in fact, is always increasing. Okay, so because we have this contradiction, this means that f of d, in fact, cannot equal to 0 when d is not equal to c. So this means, in other words, c is the only root. Okay, so that's a bit of a sophisticated proof, but ultimately it gets us to knowing that there is a root. We've proven that, and it's unique because if there is another one, then it causes a contradiction of Rolle's theorem, which is something that we just proved moments ago. Okay, so we're finally going to actually work with the mean value theorem itself. So mean value theorem, we can abbreviate it MVT. So the conditions are the same as the conditions that you need for Rolle's theorem. You need f to be continuous on the closed interval AB. We need f to be differentiable on the open interval AB. And that's all that we need at this reality. So what we want to say is that there has to be a point C on that open interval, so this is the open interval AB, where the derivative at C has to equal f of b minus f of a over b minus a. Another way of writing this is that you could say that f of b minus f of a, the difference of the functional values, is the derivative has to be equal to the derivative at c times the derivative of the x values. So the difference in the y values has to be equal to the derivative at c times the x values. Now, geometrically, what's going on here is this is the slope of the tangent line, and this is the slope of the secant line. So this is tangent, and this is secant. So if you kind of think about what's happening here, I have some function f. Let's say this is the value a, this is the value b, and I connect those with some sort of secant going between them. Then we're going to say that this has a slope. That's this slope here, right? Because that's f of b minus f of a, y2 minus y1 over x2 minus x1, right? And what we're saying is that there has to be some point C, perhaps like here, where the slope of the tangent line is the same as the slope of the secant line. And that's going to naturally occur at least one. In this case, it's occurring at 2, because there's another one, C2, over here, where it's doing the same thing. All of these are going to be running parallel. All right, so that's kind of like the geometry of what's going on here. Proving this takes a little bit of thinking. All right, so to prove this, we have to get a little bit of a geometric structure here. Okay, so we're going to put down kind of ourselves in the first quadrant. We're going to build a bit of a function f here. This is going to be the a value. This is going to be the b value. And we're going to connect these things with this secant. Right, so there's the secant that runs between them. Right? So this is at the height f of a. This is at the height f of b. Right? We're going to call this line g of x, the secant, and this one is f of x, right? So that's our function value. And we're actually going to claim a space here. So we're going to say that for some value x, h of x is the difference between these. So it's going to be f of x minus g of x. Okay, so that seems like a little strange thing to do here, but that's going to be part of what allows us to prove this. Okay, so if I use my point slope formula, right, then I know that g of x minus f of x, right? So g of x minus f of x, I'm going to write this in the point slope form, should be equal to some m times x minus a. Okay, so wait a minute, let's think about what this is, right? So, sorry, g of f, not f of x, let's fix that. G of x minus f of a, right, should be equal to m times some x minus a. So what I'm looking at here is essentially the point f at a, the point g at x, because g of x is equal to f of x at a and b, right? So that's pretty straightforward. Okay, so what's going on here? This is the secant line. These are 2 points that are on the secant line, right? So we're saying that this point minus that one should be equal to the slope of these two, right? So that's point slope form. This is some arbitrary point on the line, right? Minus the fixed point, so y minus y sub 1 is equal to m, the slope of this, times x minus x sub 1. But we know the slope of that line. See, the slope of that line is fb minus fa over b minus a. So this can be written as g of x minus f of a is equal to f of b minus f of a over b minus a times x minus a. So this is an adequate equation of that secant line given this drawing. Okay, so great. Let's do some moving some stuff around a little bit here. I'm going to move that f of a to the other side. So I'm just going to get an equation for g of x. G of x is equal to, let's see, f of a plus, right, f of b minus f of a over b minus a times x minus a, which means h, which is f of x minus g of x, so h of x is going to be f of x minus this, so it's going to be f of x minus f of a minus f of b minus f of a all over b minus a times x minus a. Okay, so we want to look at this h of x specifically at 2 places. We want to look at h of a, which is here, which we would expect that to be 0. And if you substitute the a in, it's going to be 0, because you're going to get f of a minus f of a minus f of b minus f of a over b minus a times a minus a. Well, this minus this, that's 0. This minus this is 0. 0 times anything is 0, so this comes out as 0. Okay, so let's see. Let's take h at b. All right, h at b gives me, let's see, f at b minus f of a minus f of b minus f of a over b minus a times b minus a. All right, so a little bit of looking at this. This cancels with that, which means that I have f of b minus f of a minus f of b plus f of a. This cancels with that one. This cancels with that one. And I'm again at 0. So note, h of A equals h of b, which equals 0. This is making me set up for rolls, right? Because h has to be a continuous differentiable function because it's a composition of f and things that are continuous and differentiable. So ultimately, I have what I need for Rolle's theorem. So we're going to clear out a little bit of space here and we're going to work from there. Okay, so moments ago we established that h at b is equal to h at a, which is equal to 0, which met the initial conditions of Rolle's theorem, right? Which, okay, so that tells me that there has to equal c on this interval AB, where h prime of c has to equal 0. That's what Rolle's theorem says. Now, if we recall, h is this f of x minus f of a minus f of b minus f of a over b minus a times x minus a, right? Okay, so if I take the derivative of that, no, I'm taking the derivative with respect to x. So this is a constant. This whole thing is a constant, and the derivative of that's just going to be 1. So h prime of x is just going to be f prime of x. That goes to 0, that goes to 0, this goes to 1. So h prime of x is in fact f prime of x minus, sorry, that doesn't go to 0, that's just the constant in front of 1, minus f of b minus f of a over b minus a. Derivative of that is 1, that constant comes down. Okay, so when we're at c, 0 then, because c, h prime of c is 0, right, has to equal to f prime of c minus this thing, f of b minus f of a over b minus a. Bring the this over to the other side. This is going to tell me that f prime of c is now positive f of b minus f of a over b minus a, which is exactly the mean value theorem, right? That there has to exist c on the open interval where the tangent to a point, the slope of the tangent has to equal the slope of the secant. So there we have it. This is a little bit of notes on the mean value theorem. We will apply this in some exercises in class.